Lisa Casper, and I'm an inside sales rep here at Test Oil. We are very pleased to be hosting this webinar today, and our guest presenter, Mr. Greg Livingstone of Fluitec. Before we start the webinar, there's just a few things I want to go over. First of all, I'd like to check my audio. If you can hear me, please raise your hand by clicking on the little hand icon in the toolbar on your GoToWebinar application. Okay, good. I see some hands being raised. Looks like I'm working okay. Now, the other thing I wanted to do is let you know that everybody will be on mute during the webinar. We are recording this webinar so I can share it with you later, and by keeping everyone on mute, we will ensure a high-quality recording. If you have any questions, you can submit them using the questions field in the toolbar. If we have time at the end of the webinar, we'll address your questions. If we don't have time, we will address them via email. So let's get started. As I mentioned, today's presenter is Greg Livingstone of Fluitec. Greg has been involved with lubrication, contamination control, and condition monitoring his entire career. He's a certified lubrication specialist and has held industry leadership roles in several committees, including ASTM's Turbine Oil Analysis and Problem-Solving Committee and STLE's Power Generation and Wind Turbine Technical Groups. Greg has authored more than 40 published papers focused on lubrication condition monitoring and contamination control. Thank you for joining us today, Greg. I'm going to pass the controls on to you now.
Excellent. Okay. Well, thank you very much for the introduction, and thank you to all of you remotely online here that are watching this. I'm pleased to be talking to you today about lubricant deposit characterization. I think this has been a particularly interesting subject for me for the last several years, and one of the reasons is that many times when people see deposits, or when I see deposits in lube systems, you assume it's one thing, and then when you go through some analysis and you start to gather data about it, your assumptions are thrown out the window and you realize that it's an entirely different thing. So this has been a subject that's been an area of, there's a lot of new things that we find and discover in this. So it's been a fairly interesting area to study. Well, we know that lubricant deposits cause a whole host of different problems. And essentially, lubricant deposits are derived from various different stresses on oils that will degrade and change molecularly the components of the oil so that these new degraded components are no longer so stable in the oil, and they will come out of solution and form deposits. And these deposits can cause a whole host of problems. They're sticky in nature often and can cause components like valves to stick. They can plug up small oil lines and actually restrict oil from flowing in certain parts of the system. Some types of deposits can slime over filters and result in premature filter life. Deposits and varnish in particular is a great insulator. So we find that it can coat heat exchangers and really lower the efficiency of heat exchangers. We also see that because of the insulating characteristics of varnish, it can cause elevated bearing temperatures, for example. And in addition to elevated temperatures in bearings, sometimes we see that the lubrication regimes can be altered by varnish. And we may actually go from a full film supporting the bearing to maybe a mixed film, and in some cases we've seen metal-to-metal contact. And then we've also seen seals failing as well as a result of deposits. So deposits can cause all sorts of problems. The point of this is, why do we actually want to characterize these deposits? In most cases, people will see, they'll see sludge and varnish in the system and assume that it's the oil's fault, and then leave it at that and change the oil and go on. There is a lot of really valuable meaning that can be derived from characterizing these deposits and doing some analysis on them. The first thing is, if you are understanding why your fluid is failing, this is kind of the root about around putting a condition monitoring program together. So if you understand that various different failure modes that are occurring in the fluid, you can add additional tests onto your condition monitoring program that will specifically be looking for those modes of failure. If you can identify the root cause of your fluid from failing, in many cases, there are some solutions to this. So if you can, in fact, identify why the fluid is failing and correct that, you're going to end up with fewer deposits in the system, longer lasting and higher performing lubricants. And ultimately, from this information, from actually analyzing these deposits, you want to take proactive action to try to improve the life and performance of your lubricants. So how do we go about analyzing these deposits? The first thing is, the easiest way is appearance. And we find that these sludges and varnishes and lacquers and the goos and various other terms that people call for deposits, these come in a wide range of different physical appearances. So we see gooey varnish and sticky varnish. This was an extremely sticky varnish, spongy, powdery varnish, chunks of varnish. We see some burnt appearances, some gelatinous type varnishes, and we also see some really stretchy, gooey, stretchy varnishes as well. So we see a wide range of different appearances. We also see a wide range of colors. So everything from reds to grays to oranges and purple. This is one of my favorite ones here. A nice bright purple one. We've seen green deposits and many different shades of brown. And so the problem is that this is not a very accurate way of characterizing the deposit. If you say a red gooey varnish, it still doesn't give you that much insight as to what's causing the varnish and why it's there. So the current practice is that, in general, most people just assume that all varnishes or deposits are created equal. And visual characterization is a primary mode of classifying what kind of varnish it is. And so if you see brown varnish in one system and go to another system and see brown varnish, well, often people just assume that they're the same types of varnishes. And this is actually an incorrect assumption. And so one of the recurring themes you may hear today is that it's easy to make assumptions, and it's natural for us to all make assumptions based on our previous experiences. Certainly that influences how we see things in the present, but often these assumptions are wrong. So we really we try to encourage you to try not to assume and have analytical data point the direction on as to what may be causing these problems. So one other point that I want to make here is that, and if there's any takeaway that you get from this presentation, if there's one thing that you remember, I'd like to encourage you to remember that lube systems are typically out of sight and out of mind until there's a problem. And it's really hard to actually see what's going on inside these systems. They're closed, and there's there could be all sorts of different stresses on the fluid that are really not so visible while the system's operating. When the system is down during an outage, components are opened up, and you have the opportunity to get into a system, if you find any kind of funky looking deposits or types of varnishes, don't just clean it off. Take some photographic evidence of it, capture a piece of it, put it in a bag, and I'd highly encourage you to just spend a little bit of money to get it analyzed and just to get it's a unique opportunity to provide some much deeper insight as to actually what's happening in your lube system when it's operating. So there could be a wide range of different mechanisms that can be beating up oils. And often people assume that oils are aging and varnishes are being formed due to oxidation. And oxidation certainly is one of the key modes of fluid degradation. Oxidation is a fairly slow reaction, and essentially is a reaction of any substance with oxygen. And then there are several things that could speed up the rate of oxidation. Air, of course, is one. Air containing oxygen. So oxygen being a primary ingredient for oxidation to take place. There are certain metal catalysts as well that can speed up the rate of oxidation. And then another cousin to oxidation would be ultraviolet. And so UV light from the sun, you may think, well, my oil is not really getting, it has any potential chance of having UV exposure. And in most cases, you're right, in an operating system, that's correct. Sometimes there are sight glasses that could be exposed to UV degradation, and it could rapidly accelerate degradation of a tiny, tiny bit of oil in a sight glass. But the one thing that a lot of people don't take into account is that when you're actually in the field drawing samples, before you take that sample and ship it off to the lab, make sure that that it's not exposed to UV light, because UV light really can influence and in some cases really accelerate degradation and can influence the quality reports that you get back from the labs. One other quick note about ultraviolet degradation. Often we see poly totes that are used for storing material. If you store poly totes of new oil outside for a period of time in the sun, then that also can be a form of a rapid fluid degradation. In fact, we've seen some new oils that have failed once they've been put in use because they were stored outside in poly totes for too long. So it's just a form of degradation to be aware of. Thermal degradation is an event that happens much more rapidly than oxidation. So although it's similar and it's a temperature, highly temperature influenced, thermal degradation typically requires temperatures in excess of 300 degrees C to really cause a thermal degradation reaction. And so most people think that, well, the operating temperature in my system is 140 degrees F or 65 degrees C. There's no place in the system where it's going to see temperatures that are in excess of 300 C or 500 F. But in fact, there are some events that can happen that can create localized micro temperatures that can be very, very high. And so some of these events include spark discharge, which is the accumulation of static electricity and then the release of the static electricity somewhere in the oil. And we have seen more and more spark discharge events happening in the field. And predominantly this is because a lot of new oil formulations now are more highly refined. We've seen a fairly major trend to switch from an API Group 1 solvent refined base stock to a more highly refined hydro-treated base stock with far fewer impurities. But also when you remove some of these impurities, you make the oil more non-conductive and more prone to spark discharge. So this is one form of thermal degradation to be aware of. Microdieseling is another one. Dieseling essentially can happen in a diesel engine, or it can happen in a microdieseling event, often in hydraulic systems where you have very high pressure on air bubbles and you're collapsing air bubbles. Occasionally we'll find hot spots in a system that are so hot that it's causing thermal degradation, and combustion as well can certainly be a form of thermal degradation. Well, another thing that can speed up or promote or contribute to deposits are contaminants. So certainly water contaminants, additional solid contaminants. Gas is a contaminant as well. As we see a lot of this in compressor applications where some of the processed gases can get into the lubricant and cause some unique reactions and help accelerate the formation of deposits. And incompatible liquids as well. Not only incompatible cleaners and detergents, but also incompatible lubricants could inadvertently be mixed into the fluid. And then my favorite category is maybe the other category, where I just have 4 here, but you could have a wide range of other reactions that can cause the fluid to degrade and form deposits. So additive dropout could be one. additive reaction byproducts. Sometimes we've seen issues with formulation quality. So this could be a wide range of various other mechanisms as well. So, and I would say this is just a quick snapshot of some of the different ways that fluids will degrade. So we actually get some deposits. We want to analyze them. What do we do? So this is a very basic overview of actually how we analyze deposits. The first thing is we want to try to separate the deposits from the lubricant. And in the ideal case, you have a sample of used oil and you have a baggie filled with deposits, or some deposit as well that's isolated already from the lubricant. If not, there's a lot of different things that can be done to separate from the deposit from the lubricant. So you can physically, through a physical process or a filtration process, you can separate out the deposits. You can use a solvent extraction or a chemical process. But ideally, you want to have a lubricant to analyze and the deposits to analyze. And in both cases, you want to understand the inorganic or non-organic components of the oil and the organic components of both the oil and the deposits. So common tests that are often run to look at the non-organic components in the lubricant is elemental spectroscopy. That's a very powerful tool. And for a transform infrared analysis. And infrared analysis allows you to look at the essentially the molecular fingerprint of the oil, and it provides a really nice insight into the organic constituents in the product. And we do the same thing as well with the deposits. We look at XRF. X-ray fluorescence can be a very powerful tool to look at the non-organic components in the product, and also infrared analysis again can be a good tool for us to look at the organic components. So we try to gather as much information as possible from the lubricant, as much information as possible from the deposit, and then we put our CSI investigative hat on, and we try to piece all of this together, compare the results, and try to characterize and classify the lubricant. But essentially what we're trying to do is take all of this evidence from the lubricant and the deposit, and then use this evidence to try to piece together historically what may have happened to cause this the fluid to degrade in a certain way and this deposit to be created. And ultimately, through this process, we want to try to determine the root cause of this. So how do we go about classifying these deposits? So we thought it would be interesting, instead of just saying we have a brown gooey varnish, to actually create some classification bins, so that when you do some analysis, you actually have some bins that you can say, this is the deposit can be classified by these certain physical characteristics and this source of formation. And so based on this information, we can take some proactive measures, ideally, to see if we can eliminate deposit formation. So this is the classification bins that we have put together in our classification chart for deposits. So the first level, we're trying to characterize the chemistry of the deposit. And so we can do that by looking at the organic components. In a lot of deposits, we see both water and lubricant in the deposit. And as well, there are non-organic deposits, or non-organic constituents. We can take this one more level down as well, and see if we can also kind of characterize the source of the deposit. So on the organic side, we've created 6 different buckets that can help narrow down the source of the organic deposit. And so formulation derived is one. Thermoplastic is another. Thermoplastic is a unique physical characterization of a deposit that's typically formed through spark discharge. So if you have a thermoplastic-like deposit, it is most likely due to spark discharge in the oil. Thermal decomposition, if there is strong signatures of thermal decomposition in the fluid indicating high temperatures, we would see that here as well. oxidatively derived, contaminant derived, and every once in a while we see bugs that are actually in the oil, and some of these microbes can cause a bunch of problems, including filter sliming, but you may actually have some kind of biological contaminant in there as well. In some cases we've seen in food manufacturing facilities, we've seen some biological contaminants enter into the oil and end up in the deposits. On the non-organic side, we also have formulation derived. So an example of this would be, for example, zinc alkyl dithiophosphat. ZDDP is a very common anti-wear agent used in hydraulic applications. And as that molecule gets consumed and then starts to react, it will form some phosphates and sulfates, and these are inorganic components in the deposit that are formulation derived. Inorganics as well is another type, and inorganics is essentially free of carbon. Non-organics is kind of a general category of deposits that don't exhibit organic-like nature. So they're not really, they're insoluble in highly polar solvents. They don't exhibit carbon hydrogen spectrals. Inorganic truly are free of carbons or any kind of carbon in it. And then we have three different categories that are all quite similar: soot and coke and coal. And soot is typically, these are all carbonaceous products, and again, we classify them as non-organic because they do exhibit non-organic-like behavior. And soot we classify as carbonaceous products that are less than a micron in size, and in often cases we're seeing soot particles that are much less than a micron in size. Then coke are deposits that are greater than a micron in size, and then coal is another non-organic constituent as well that is greater than a micron in size, but it does have solubility in some polar solvents, and typically we see coal dust as a part of deposits in coal-fired power plants and other places that are close to coal. So these are all nice, neat, easy to understand classification bins, but in the real world, when oils degrade and deposits are formed, deposits actually don't fit nice and easily into these various different bins. And in most cases, we see several different types of deposit that are in the fluid, that are making up the deposit. And so this is an example of a compressor. This compressor was undergoing a lot of stress. And as you see, we have some organic constituents. There was evidence of spark discharge. There was a lot of evidence of thermal decomposition. The product is oxidatively derived. On the non-organic side, we had some dirt in the product, in the deposit. We had some soot-like contaminants, carbonaceous products that were less than a micron in size, and coke-like deposits that were greater than a micron in size. Needless to say, this fluid was exposed to multiple different mechanisms, degradation mechanisms, and formed a lot of deposits fairly quickly. But this is just an example to show that you can, in fact, have multiple different types of deposits that are in a system. So if you're at a plant and not at a laboratory, you may think, well, this is all interesting, but how does this actually relate to me, and how can this help my operations? And so I want you to keep in mind, this is beyond academic. There is really some high value in trying to better understand why your fluid is failing and why deposits are being formed. So to try to illustrate this, I put together a few case studies. And so over the years, Test Oil as well has done many case studies on this. We have done many case studies on this, and but I tried to pick some case studies that were that some assumptions had been made about why the deposit was formed, and in fact some of these assumptions were originally wrong. So I have a case study here on a gas turbine tar balls, what we call tar balls, and deposits in a nuclear power plant, EHC system deposits, and another one from a gas turbine with a lot of deposits in the reservoir. So to start off, our first case study is a gas turbine that had they had a very good oil analysis program in place, but they noticed before an outage that one of the sample bottles, one of their samples was very cloudy, and if you let that sample sit for a period of time, the varnish potential, the membrane patch colorimetry test was alarmingly high. The product got cloudy. And they were coming into an outage, and they were aware that that in many cases these organic contaminants may be in solution while the gas turbine is operating, but when they come out for an outage, the reservoir cools down. Here is the time where a lot of these deposits can come out of solution. So they were alarmed going into this, and well, sure enough, they had cause for concern. And when they went into their outage, and when they immediately what they saw is these little balls floating on top of the reservoir, and the filters started plugging up very quickly. And so they noticed specifically when the oil dropped below 32 degrees Celsius that suddenly their hydraulic filters were starting to plug. Their main lube oil filters were starting to plug, and they had just a lot of deposits in the system. So they brought an oil reclamation company in, and they went through a lot of filter bags and a lot of filters to try to clean all of these tar balls out of the system. And certainly in this case, it makes sense to do some analysis and figure out what actually caused this. So we split the deposit into a few different fractions and analyzed them to see if we could try to identify some of the different chemistries. And so the first thing we observed is that there was a strong signature in the infrared analysis that was that pointed to an amine antioxidant that was part of this. And so this is an example of an infrared spectrum, and essentially what we are looking at here is the concentration of chemistry on the y-axis and the amount of the type of chemistry on the x-axis. So here we see a particular type and a particular amount of chemistry. And so in this case, what we did is this is one of the varnish fractions, and we overlaid a new amine antioxidant on top of this. And you can see in many cases here, there's an overlap and a matching here of some of the degradation components in the deposit versus the new amine antioxidant. So this particular amine antioxidant is called a phenol naphthylamine, and you can see there's a fairly close overlap here. And it was interesting, we saw both reacted and unreacted amine antioxidant here. So part of this deposit was because of a particular antioxidant that was in here. But you know, there's a lot of oils that may use this antioxidant that it's still extremely rare to see these types of tar balls formed. So clearly this was not the root cause of the issue, even though this did contribute a lot to the deposits. Another thing that we found in a second fraction of the deposit was a foam inhibitor. And this type of foam inhibitor was a polymethacrylate type foam inhibitor. It was actually not in the new product. And there was a fairly high concentration of this foam inhibitor that was in the deposit. And so since this could not be observed in the new it couldn't be observed also in the in-surface oil or in the new oil. So somehow this deposit or this foam inhibitor had entered into the system, and so ultimately when we pieced all of this together, we found some strong evidence of formulation-derived organic contaminants. So this was the amine antioxidants. We found some foam inhibitor. So this would be a contaminant-derived organic constituent. And ultimately, what we found is that there was an incompatible fluid that was inadvertently put into the system. And so the result of this is that the plant put together or improved their quality control program to not only ensure that non-compatible lubricants don't accidentally get added into the system, but they also started testing all of the new oil deliveries to make sure that, in fact, they were what they had bought was, in fact, what was being delivered. So the next one is in a deposits that were found in a nuclear power plant. And so those of you that either work in the nuclear power industry or have some involvement with nuclear power plants, you'll know that these are extremely safety conscious plants. So in fact, in my home state of Arizona, last year the safest industrial place to work in the state was actually at the nuclear power plant. So they're extremely safety conscious. And so all of the major safety systems are tested on a regular basis. And in this particular case, there's a feed water pump that had a valve, and they did a routine monthly test on it, and they stroked the valve. And the first time they tried to stroke the valve, it stuck. They immediately did it again, and there was some vibration and some sticking, and finally it kind of freed itself and could move. And then they tested it a third time, and it moved without a problem. However, this was deemed a big enough safety concern that they actually shut down one of the units for 30 hours to investigate, to ensure that, in fact, there is no possible safety issue that could have been caused by this. So this was there were 700 gallons of turbine oil that were used in this application. The interesting thing is that this particular plant has a phenomenal condition monitoring program. They were doing some very, very good tests every month, and the varnish potential test, the membrane patch colorimetry value was at a 16. Typically, anything below 16 would be classified, certainly in this application, as normal and would not be cause for concern. And so we gathered some deposits and tried to identify what actually could have caused this. So we were able to remove and analyze the deposit from the valve surface. You can actually see by the time we got the valve, there's actually just a very small amount of varnish that hadn't rubbed off that was still there, but we were able to extract and analyze that. And the other thing is the membrane patch colorimetry test, although it was only a 16, we were able to concentrate a lot of these deposits out of the oil to see if we could try to identify the same chemistry in the oil that was actually on this valve block. And we did that. Typically, the MPC test is run by putting 50 milliliters of oil with 50 milliliters of solvent. In this particular case, we put several hundred milliliters through this patch to try to capture as much material as possible to analyze. And we analyzed both the deposits, and we analyzed the deposits in the valve and the deposits pulled out of the oil, and it matched. The interesting component of this, though, is that there was a very unique signature that we identified in the infrared analysis. And this, these two little doublets here indicate that there's a molecule in here, or a substance called a primary amide. And we also saw a lot of evidence of carboxylic acids. And so carboxylic acids are a very common type of degradation mechanism through oxidation. And so if you look at how amides are created, they're typically created, there's just a small number of ways that this type of chemistry could have been created. And one reaction is the formation of ammonia with acids, and certainly we see here there are some carboxylic acids that are present in the oil. So certainly there's some acidic components here that could cause this reaction. However, it wasn't initially clear where ammonia or how ammonia could possibly have gotten into the system. But what we found is that, so if we want to classify this as oxidatively derived, we did find some evidence of carboxylic acids, and contaminant derived. And in fact, what we identified is that there was chemistry in the steam that, and inadvertently, every once in a while, it's very hard to prevent steam leaks from ever occurring in these systems, but there was a steam leak that happened in this particular system in the past. The chemistry in the steam reacted, and there's ammonia type chemistry in the steam. It reacted with the oxidation products, the acids, and created this fairly unique chemistry. And so this was the first time we had seen this reaction creating these primary amides. And since we've seen this in many different scenarios, not only in steam turbines due to steam chemistry, but also in compressor applications, certainly compressors that are compressing ammonia that could accidentally get into the oil as well. So I guess one of the things is, why is it important for us to dive into so much detail to see if we can understand what's happening here? And in the case of this the nuclear power plant, it was really important to see if they could identify why this happened, so that their condition monitoring program could also be able to detect this in the future, and they could prevent this from happening in the future. So in this particular case, it's not actually possible to eliminate any chance of ammonia from getting into the system again, but actually there are technologies to be able to remove oxidation byproducts and remove some of these carboxylic acids. And the second big conclusion from this is that, in addition to the MPC test, looking at the amount of carboxylic acids as measured by infrared, and also looking at the formation of this little doublet that we saw in the infrared fingerprint and the formation of this amide, this actually becomes a very important condition monitoring tool. So in this case, diving into the detail to figure out what caused this reaction was really a very proactive measure to make sure that the proper tests are performed going forward to make sure that this type of deposit doesn't happen again. This is also another example of a deposit that you can, in fact, eliminate this type of deposit from happening in your system, either by getting rid of the carboxylic acids or by getting rid of the ammonia. In this case, it's probably hard to get rid of the ammonia, but the acids, there are technologies available that can remove acids and can essentially, if you remove this component from the equation, you're not going to have this kind of formation happen in your system. All right, the third one is from an EHC system deposit. Electrohydraulic control valves are used in steam turbine applications to control various different aspects of the steam turbine. And in many cases, so we've looked at a lot of EHC fluids before, and in most cases, this application requires a fire-resistant product, so often phosphate ester, in almost all cases, phosphate ester fluids are used to as a lubricant in these systems. So the plant was experiencing rapid filter plugging and actually had an outage due to a lot of dark deposits that were in this fluid. And so we've seen this, and we've seen this many times. In fact, there was a very, very good EPRI report that was produced 10 years or so ago that discussed the formation of black deposits in phosphate ester fluids. So it's a well-known phenomenon. And typically when I see this, I assume it's microdieseling. There are some types of, there are some systems that are particularly prone, some EHC system designs that are particularly prone to microdieseling it forms black soot-like material. It will make the fluid black. Typically, these are submicron particles. And so we saw this, and my immediate reaction was, well, I'm sure this is microdieseling. However, we did some further analysis on this, and in fact, we did see a strong evidence of carbonaceous black bodies in the fluid. One interesting thing you can note here is that you can actually see this. The red line here is the spectra of the new phosphate ester fluid. And then you see the baseline has been depressed significantly here, and this is of the deposit. And this is indicating that there are some black bodies that are actually settling out onto the analytical instrument and are causing this spectra depression here. So we knew that there was some kind of thermal degradation happening. We knew that that it was a black carbonaceous type material, and so we thought, well, it's probably one of three things. It did not exhibit any thermoplastic-like behavior, so we ruled out ESD, and so we narrowed it down between microdieseling or some kind of high temperature reaction. And again, in most cases, I would have just assumed it was microdieseling, and we're looking at submicron particles. Well, one simple way of classifying the different sizes of these particles was to do a paper chromatography experiment. And this will really be useful in helping identify and separate out different sizes. And so we did this, and essentially very, very small particles are going to go right through this, this large filter paper. Unless there's varnish in there that causes it to be sticky, and then it creates some interesting rings on the chromatography paper. But in this case, there was no evidence of varnish, and all of these black-like materials were actually captured on this filter paper, indicating that, in fact, these are particles that we're dealing with that are greater than a micron in size. So it ruled out soot-like contaminants or microdieseling. We did some photographic examination of this as well, and in fact, most of these particles were greater than 5 microns in size. So in this case, this was a thermal decomposition product that, in fact, was not from microdieseling. And the conclusions from this, in fact, we dove into non-microdieseling problems that could be contributing to this. We actually found there was a malfunctioning pump and a valve that was producing some extremely high temperatures in the system and were causing accelerated degradation and causing the formation of these coke-like products. So this allows the plant, the common fix for microdieseling in these EHC applications is to switch from a fixed volume pump to a variable speed pump. However, this is a pretty expensive upgrade, and in this particular case, had we not done this analysis and the plant invested all of the money to put a variable flow, a variable speed pump in place, it actually would not have solved this problem. So this actually turned out to be a very useful analysis to allow the plant a course of action to solve this problem. All right, so my fourth and final case study here is in a dirty gas turbine reservoir. And over the years, we have seen many, many different reservoirs. When the oil's, during outages, the oil's been evacuated, we've seen a lot of sludge over the years. And in this particular type of gas turbine, I've seen lots of different sludges and deposits, and sure enough, when I saw this deposit, I thought, okay, well, this is a common varnish that we typically see in these large frame gas turbines. And but however, we still try to do some analysis on this. The first clue that made me think maybe this is a little bit different varnish than what we've seen before is that during the outage, the power plant had a crew in that was doing confined space tank cleaning. This guy was not having such a good time. So he was scrubbing away trying to remove these deposits, with virtually no impact whatsoever. And he was having a hard time. And so we thought, well, maybe there is something a little bit unique about this. So we did some analysis on this, and sure enough, we found that there was actually this deposit was predominantly a foam inhibitor. And you can imagine actually a fair bit of foam inhibitor that had come out of this turbine and out of this turbine oil and caused all of these deposits. And the interesting thing is we really just saw the deposits in the reservoir, and reservoirs are perfect places for deposits to form. And but it allowed us to better understand why the deposit was there and what it was made up, or what made up the deposit. But also from a course of action, a corrective course of action, the plant had to decide: do we extend our outage and have a big complex chemical flush come in and try to remove all of this deposit before we put a new charge of oil in? It would have extended their outage a couple weeks. It would have been very costly. In this particular case, the oil was not absorbing any of this or dissolving any of this particular foam inhibitor. You could see how hard it was to try to remove this foam inhibitor. So the plant put, the rest of the system was clean, and the plant put new turbine oil on top of this deposit that was in the reservoir. And quite honestly, there's been no problems whatsoever with this, but at least by going through the analysis, they were able to understand what the deposit was and understand their risks of what course of action they should take. So in conclusion, there are many different modes of fluid degradation. And understanding how your fluid is failing and why it's failing is really important. And a key part of this is trying to extract as much evidence as possible from your deposits. And your condition monitoring program, therefore, can be the basis of your analysis on uncovering why your fluid is failing. So you should really try to tailor your condition monitoring program to match the mode of failure in your system. And also understanding the mode of failure allows you to address the root cause. And most importantly, the last point I'll make is don't make assumptions. And certainly you have heard this advice, I'm sure, before, but these are our 4 case studies here where our original assumption after going through and doing analysis was in fact not correct. So this is another good area in life to keep in mind. Don't make assumptions in this, and let data drive your decisions. So thank you very much for listening in on this, and I think we've scratched the surface here on deposit characterization, but at least it gives you maybe a little bit more information that if you find some deposits in your system, capture them, send them to your laboratory, and try to capture some data out of that.
Excellent.
So do we have okay.
Go ahead.
Do we have time for a couple of questions? Are there any questions that popped up that we should look at addressing, Lisa?
We don't seem to have any questions currently, Greg. If you want to add some questions, we do have a couple of minutes here. If not, you can always send any questions. We can answer them via email at any time. Rest assured, we will get back to you and get you the proper answer.
Okay, that sounds great. So yeah, I think that this can be a very complex subject, but I think the big takeaway is that there is value in your deposits. Capture it, send it to your lab, and the lab, your oil analysis lab, can really help give you a lot more insight into the quality of your oil. And I just want to make a couple special acknowledgments as well. Dr. Dave Wooten he's been involved in all of these root cause analysis with me, and we've co-authored multiple papers on this subject together. So I want to acknowledge Dr. Wooten's involvement in this, and also Test Oil has done a lot of laboratory analysis to support this as well, and has developed what I think is really a leading deposit characterization analysis package. So I want to acknowledge both Tess Oil and Dr. Wooten in this.
Thank you for that, Greg. We do have a couple of questions. We've got a couple here, so we'll address as many as we can. Greg, the first one is, in an EHC system that has a PAC fluid, EcoSafe, which has no hydrocarbon in this fluid, what can cause a varnish-like deposit, which was characterized as being a carbon deposit?
Ooh, that is a good question. Well, so PAGs are sometimes considered to be deposit-free type formulations because they are so nonpolar in nature. But in fact, we have seen, especially in EHC applications, deposits derived from PAGs. So there's a couple different things that could be causing this, but in most cases, we find evidence of hydrocarbons in the deposits that have reacted with the PAG chemistry, and certainly PAGs are highly incompatible with mineral oils and other fluids, and so we have seen evidence of incompatible reactions that happen. So even though you may not see any evidence of mineral oil contamination or hydrocarbons in the PAG fluid, there may in fact be evidence of hydrocarbons in black deposits. And the second thing that can cause black deposits is very high temperature. PAGs are not immune from thermal degradation. So if in fact there are high temperature thermal events, it can cause some dark looking deposits that look like very, very dark deposits. And this would be in absence of hydrocarbons. So that's another thing to consider as well. There may in fact be, like the EHC application or the case study that I showed, microdieseling was in fact not occurring. It was a very high temperature, localized high temperature event that caused the fluid to degrade. And so those are two areas that I would consider pursuing in your investigation. Ultimately, you should get a sample of the deposit to your lab to do some further analysis.
Excellent. Thanks, Greg. Okay. Next question is deposit analysis typical of most oil analysis programs?
Unfortunately, it is not, but predominantly because it's much easier to get an oil sample than it is to get a deposit sample. It is possible to try to separate out these solid or these components, these degradation components in the oil that can be contributing to deposits. So it is possible to do some separation processes on the lubricant to analyze, but that's not often done. Ultimately, there still may not be a correlation between deposits that are actually in the oil and the deposits that are actually in your system. So ultimately, it's best to try to get and capture a deposit from your system and send that off for analysis. And unfortunately, the only available time that most people have to be able to capture these deposits are during outages. But even still, during outages, this is not a common form of analysis, but because there's such high value that can be derived from this, it's something that I think should be done more often.
Thanks again, Greg. Okay, we do have a couple more questions, and I think they seem a little more complex, so if we can save them and reply back via email, that would be great. We appreciate your patience.
Okay, all right.
And yep, we want to thank you all for attending the webinar today. And in just a few hours, you'll receive an email with the survey and a link to the recording of the webinar, so you can come back to it anytime. Have a great day. Thanks again for joining us. And thank you, Greg.
Okay, thank you.
Thank you.